Welcome to BioNerds and Engineers, where biology meets engineering. We explore the journeys of scientists, engineers, CEOs, and innovators through expert conversations and deep dives into groundbreaking research. Make sure to subscribe now to stay ahead in the world of innovation, technology, and leadership. All right, let's jump straight into today's explainer. We are looking at something that is literally keeping data center architects awake at night, and that's the absolute explosion of energy required to power the AI boom. We're going to break down exactly how engineers are battling these massive power demands to secure the next 10x growth in tech.
That's right, Irvi, because right now infrastructure scaling is hitting some very hard, very real physical limits. We are looking at an engineering challenge on a scale we honestly haven't seen in decades.
Let's put this into perspective for a second. If you do a normal web search, it uses a tiny amount of power, about 0.3 watt-hours of electricity. But the moment you type a prompt into a generative AI model, you are suddenly using about 2.9 watt-hours. That is a staggering 10x energy jump for just a single query. And when you multiply that by billions of users asking AI for dinner recipes, coding help, or to write their emails every single day, you get a massive, massive multiplier effect. Which naturally leads us to the big question. Is this going to break our power grid? The reality check here is pretty sobering. By 2026, global AI data centers are projected to consume over 1,000 terawatt-hours of electricity. To put that completely astronomical number into perspective, that is roughly equivalent to the annual electricity consumption of the entire country of Japan. It's not just a software scaling problem anymore, it is a fundamental electrical constraint.
An entire country. That is just wild to think about. And looking at the US specifically, the numbers are just as dramatic. We are looking at a jump from 176 terawatt-hours in 2023 to up to 580 terawatt-hours by 2028.
Exactly. We have nearly 23 gigawatts of new computing capacity coming online over the next few years. If this trend holds, AI data centers could eat up to 12% of the entire US power grid.
And you can't just flip a switch to generate that kind of power overnight.
So let's get into Section 1, Training versus Inference, the real culprit.
So where is all this energy actually going? Let's clear something up, because there is a huge myth out there that creating these models, the initial training phase, is the main problem. But that's really only half the story.
Right. Training a frontier model is incredibly energy intensive. We're talking 50 to 62 gigawatt hours of power. But it's a one-time sunk cost. The real culprit is inference, which is the model actually running and answering user queries in real time. Because of the sheer volume of global traffic, inference now accounts for 80 to 90% of total AI energy consumption.
It's basically like starting up a giant gas-guzzling car engine. Starting it takes a massive burst of energy, sure, but leaving that engine running forever at a red light while billions of people hop in and out of the car, that continuous drain is what's actually emptying the tank.
And that tank is draining faster as the tasks get more complex. Text generation is a 10x multiplier over normal search. But image generation takes 20 to 40 times more compute than text. And generative video? That is 1,000 times more computationally heavy. On top of that, we have new reasoning models that think through multiple steps before answering, which exponentially compounds this energy drain and pushes our current hardware to its absolute physical limit.
Which brings us to Section 2, Cooling the Beast, Liquid and Immersion. Okay, so with all this hardware running at maximum capacity, how do these facilities keep from literally melting down? Because traditional air conditioning physically maxes out at cooling about 15 kilowatts per server rack.
Basically air cooling is dead for AI hyperscalers. The engineering pivot here is liquid cooling, specifically two-phase immersion cooling. We are literally sinking servers into sealed tanks of thermally conductive dielectric fluid. Because liquid transfers heat so much better than air, it absorbs 100% of the heat and allows us to run extreme rack densities of over 100 kilowatts. It drops the power usage efficiency, or PUE, down to a near-perfect 1.03.
And what I absolutely love about this is the silver lining. These immersion systems produce a much hotter exit liquid, somewhere between 55 and 70 degrees Celsius. Engineers are realizing they can actually reuse this waste heat. We can flip data centers to be water positive and carbon negative by piping that exit heat into thermal water purification systems for desalination, or even using it to power direct air capture systems that pull CO2 right out of the atmosphere.
Let's move to Section 3, Rewiring Silicon, Neuromorphic and Photonic Chips.
Now, cooling is amazing, but it's still just a thermodynamic band-aid. If we want a real cure for this energy crisis, we have to do a fundamental architectural overhaul of the silicon itself. We have to look way beyond traditional GPUs. This brings us to neuromorphic computing. Traditional chips suffer from the von Neumann bottleneck, basically wasting energy shuttling data back and forth between memory and the processor. Neuromorphic chips are biologically inspired. They use artificial neurons and synapses processing data via spiking neural networks. They only fire when there's an event, exactly like a human brain. IBM's True North chip, for example, operates on just 70 milliwatts. That is a fraction of a single watt, compared to massive megawatt supercomputers.
And if brain-inspired chips aren't sci-fi enough for you, let's talk about photonic neural networks. Instead of pushing electrons through copper wires, these chips use lasers and optical components to process matrix operations using the speed and parallelism of light. Light doesn't have electrical resistance, which means it completely removes the resistive heat generated by moving electrons. It essentially conquers the thermal wall that is holding back our current hardware.
Moving right along to Section 4, Edge AI and Algorithmic Efficiency.
But hardware is only one side of the coin. Let's pivot to software and local processing for a minute. Do we really need to send every single AI query thousands of miles away to an energy-hungry cloud data center?
Not at all. There are massive efficiency gains to be made in the algorithms themselves. Take a look at the Nokia Energy Efficient AI for Networks guide. They've proven that by aggressively optimizing software, we can slash energy needs dramatically. Techniques like model pruning literally remove redundant neural connections, and quantization drops the mathematical precision from 32-bit floating point down to 4-bit integers. Just applying those strict software constraints can slash AI energy needs by up to 91%.
And when you make the software that efficient, you unlock Edge AI. Instead of relying on the cloud, we can deploy inference directly onto local smart sensors, wearables, and microcontrollers. This keeps the processing local, it drastically reduces the strain on network bandwidth, and it saves massive amounts of power by just avoiding that constant back-and-forth cloud communication.
All right, our final stop. Section 5, Power Generation, Geothermal Data Centers.
So we cool the chips, we redesign the silicon, and we shrink the software. But that leads to the ultimate big-picture question. Even with all these incredible hardware and software efficiencies, we still need gigawatts of power. Where does the clean, 24/7 baseload power actually come from to feed these hyperscale facilities?
Well, solar and wind are great, but they are intermittent. AI data centers need constant, uninterrupted power. Enter Enhanced Geothermal Systems, or EGS. Traditional geothermal requires finding rare, natural hot springs, but EGS takes advanced drilling technology, stuff originally developed in the oil and gas shale patch, and uses it to drill deep into dry, hot rock practically anywhere. We inject cold water under high pressure to fracture the rock. The earth heats it up, and it returns as steam to drive continuous 24/7 power turbines.
This is a total paradigm shift. It moves geothermal from a niche geographic luxury into a highly scalable, low-carbon reality. And it's not just theoretical either. Tech giants like Google and Meta are already backing commercial EGS projects in the US right now to power their data centers. It's just this perfect marriage of old-school, heavy industrial engineering powering next-gen artificial intelligence.
Ultimately, it's going to take all of these. We aren't going to solve the AI energy crisis with just one magic bullet. It requires a highly complex mix of advanced thermodynamics, novel chip architectures like photonics and neuromorphics, heavily optimized software, and scalable green baseload power like EGS.
It really is the ultimate engineering challenge of our generation. Well, if you enjoyed this explainer and want to keep exploring how biology meets engineering, make sure to like, subscribe to BioNerds Engineers, and tell us in the comments, what solution do you think will win in the AI energy race? See you next time!